Here we're going to look at question 18 from section 2 of the ENGAA specimen paper. In this question, we're given the following circuit, which has two different power sources, one of a power of 20 volts and one with a voltage of 10 volts. And these are connected with resistors of 40 ohms in different positions, with a voltmeter reading with a reading of V0 around one of the resistors, and an ammeter through the middle of the circuit with a reading of A0. So the question it asks us to do is to find these values V0 and A0. Now if you'd like to have a good go at doing this question yourself, then please pause the video now. Otherwise, let's get on with it. So looking at this question, we can see it's a bit odd because we have these two different power sources and they seem to be connected to different parts of the circuit but flow together into this one part here. So a tip which I have for any question you get which looks like this at all is to try and label all of the currents on your circuit. So coming out of our 20 volt battery, we're going to say we have a current of I1, and coming out of our 10 volt battery, we're going to say we have a current of I2. Now this is handy because when we consider this portion in the middle, which is shared by both of the batteries, we know the total current is just going to be the sum of these two currents, I1 plus I2. So this means that the reading on our ammeter, A0, is just going to be this I1 plus I2. Then, if we want to think about the other value we have to find, V0, then we can just use Ohm's law to try and find it. The V is equal to IR. So the current through this portion is just I2, the voltage is V0, and the resistance is 40 ohms, giving us the equation that V0 is just equal to 40 I2. Therefore, to try and find our two answers, A0 and V0, what we want to try and find are these currents, I1 and I2. So, now that we know we need to find these, let's try and see if we can think of some way of doing that. Now, one thing we know is going to be true with circuits, which we're always going to be doing, which we'll do at this sort of level, is Ohm's law, and it's a really good idea to always keep this equation in mind and see if you can ever apply it. So, what we could also try and think about in this sort of circuit are going to be loops. So, we know from Kirchhoff's voltage laws that the voltage around loops is always going to cancel out, it's always going to be zero. So, for example, it means that this 20 volts across this battery has to be shared across these two resistors, and the 10 volts from this battery has to be shared across these two resistors. So, let's see if we can combine Ohm's law and Kirchhoff's voltage law here by considering each of these two loops. So, if we look at our first loop, then we can apply Kirchhoff's voltage law. So this voltage to the battery of 20 volts is going to be given by the voltage across our 40 ohm resistor up at the top here, which is I1 multiplied by the resistance from Ohm's law. And for our second resistor, our 40 ohm one in the middle here, it's just the current, which is I1 plus I2 multiplied by its resistance of 40 ohms. So simplifying this a little bit and dividing through, then we get this equation here, that 1 is equal to 4I1 plus 2I2. Now at this point, there's nothing else we can do with this equation, so let's think about our second loop over here, where we can do something very similar and say the 10 volts in the battery is equal to the current through our top resistor multiplied by the current through our resistor in the middle. So then, doing the same thing of simplifying this and dividing through, we get this equation here, that 1 is equal to 4I1 plus 8I2. So now that we've done this, we can tell that we have two simultaneous equations with I1 and I2 in them. So we can solve it to try and find these two currents. Now to try and solve these two equations, the easiest thing to try and do is probably just to take the first equation from the second, so do 2 minus 1. Now doing this, we get that the left-hand side of the equation is just 0, and that's equal to 6I2, which of course just means that I2 is equal to 0 amps, so actually there's no current at all flowing in this portion of the circuit. Now since we've got a value of I2, we can substitute it into either 1 or 2, and both cases will find that 1 is equal to 4I1, which of course just means that I1 is equal to 0.25 amps. So with these two currents, we can substitute them into our two equations which we found at the very beginning of this question, and we find that A0 is just equal to our 0.25 amps plus our 0 amps, so in total it's just 0.25 amps, and then V0 is just 40 ohms multiplied by our current of 0, which is just 0 volts. So there's no voltage at all across our 40 ohm resistor. Now these two answers, of course, are our final answers, and they correspond with answer A given the question.